name is Rick Brummett, and for my presentation for Interactive Case Study 3 for Molecular Biology, I will be explaining how levodopa and carbidopa, otherwise known as Lodocin, are used together to treat Parkinson's disease. I'll also show you how scientists visualize the structure using the UCSF chimera and X-ray crystallography. Let's get started. Starting with my first slide labeled Carbidopa. Therapy for Parkinson's disease requires carbidopa, but it is also known as Lodocin. Although it isn't the primary therapy, it facilitates levodopa's entry into the brain without causing it to degrade too quickly. Using UCSF Chimera's 3D visualization, I will examine the chemical structure, mode of action, and clinical significance of carbidopa during my presentation. Now on to my second slide. What is Parkinson's disease? Parkinson's disease and healthy brains are contrasted in the image that I included in this slide. By increasing dopamine activity in a healthy brain, it is shown by bright red and yellow in the substantia nigra and basal ganglia. However, in Parkinson's disease, this activity is significantly reduced, indicating a significant loss of dopamine-producing cells. Parkinson's disease symptoms include tremors, stiffness, and slow movement. Levodopa can help with these symptoms, but its effectiveness is limited since the majority of it is changed before it can even get across the blood-brain barrier. Now onto my next slide labeled How Carbidopa Helps Levodopa Work. By inhibiting peripheral dopa decarboxylase, carbidopa enhances levodopa's cellular effects beyond Parkinson's. My diagram shows how carbidopa activates the aryl hydrocarbon receptor to interact with the androgen receptor. This interaction ubiquitinates and degrades AR, reducing AR cell numbers. This apoptosis rises in cell migration and proliferation fall. This method shows that carbidopa prevents aberrant cell proliferation, therefore benefiting in more brain dopamine. Now onto my next slide, which is the chimera image and the structural insights of this. The UCSF chimera was used to crystallize the human dopa decarboxylase enzyme related to Carbidopa PDB entry IJS3. The beige ribbon structure shows the enzyme's three-dimensional shape, while the multicolored atoms in the middle show carbidopa interacting with the PLP cofactor. Carbidopa fits snugly into the active site and forms a covalent hydrazone with PLP. Because this process permanently deactivates the enzyme, more levodopa may reach its target and prevents it from turning into dopamine outside of the brain. Now onto my next slide, labeled The Science Behind X-ray Crystallography. This structure was solved using X-ray crystallography, a powerful technique for protein structure determination. Dopa decarboxylase was initially isolated and crystallized by researchers. X-rays were then flashed on the crystal to create a protein atom diffraction pattern. These diffraction data were used to generate a 2.0 angstrom 3D atomic model and an electron density map. This high-level detail allowed them to visualize the hydrazone interaction between carbidopa and the PLP cofactor. This shows how it inhibits the enzyme. Now onto my next slide, the importance of carbidopa. My image shows how repeated levodopa doses modify brain dopamine levels throughout the day. Without carbidopa, a lot of levodopa is converted into dopamine reaching the brain, reducing its effectiveness and increasing the risk of nausea and hypotension. Carbidopa fixes this by suppressing peripheral dopa decarboxylase, which induces early conversion. This allows more levodopa to pass the blood-brain barrier and become dopamine where needed. Cinnamon, a Parkinson's disease medication, helps patients walk more comfortably and manage dopamine levels. To conclude my PowerPoint presentation, dopamine-producing neurons die, interfering with basal ganglia transmission and causing movement and behavior symptoms in Parkinson's disease. Levodopa restores dopamine, improving muscle control and coordination. When given alone, most of it is converted before reaching the brain. Thus, carbidopa is needed to delay levodopa breakdown, increasing cerebral distribution and limiting side effects. They remain one of the most effective Parkinson's treatments when taken simultaneously. My presentation was based on the following sources, which include research publications and data from the PDP as well as the Chimera Visualization Program developed by the University of California, San Francisco. Thank you so much for watching my presentation on carbidopa and Parkinson's disease. I hope this helped you understand how this drug structure and chemistry work together to improve real-world treatments. Thank you. Have a great day.